norms are equal in a finite dimensional nonlinear space, so there is nothing much to study in finite dimensional. So we move to infinite dimensional Banach spaces or nonlinear spaces. A nonlinear space without a finite basis as a vector space is called infinite dimensional nonlinear space. So we are going to take the motivation on how we defined norm in R power n. For example, we take the one norm of R power n, we define it to be summation I equal to 1 to n modulus of xi, and now we are going to study the sequence spaces. The sequence spaces, so we consider the set of all sequences xn where we can define one norm of summation I equal to 1 to infinity modulus of xi. But since this is an infinite sum, this sum has to converge. So that is a condition we put. So in R power n we need not put this condition because it's a finite sum, but here we have to put this condition. So we define a set L1, small L1 is a set of all sequence such that summation I equal to 1 to infinity modulus of xi less than infinity. Then L1 will be a norm-linear space with this norm. We call it as a one norm defined by summation I equal to 1 to infinity modulus of xi. Similarly, we can define ell-p to be set of all sequences satisfying summation I equal to 1 to infinity modulus of xi to the power of p less than infinity, so that we can define the p norm of x as summation I equal to 1 to infinity modulus of xi to the power of p to the power of 1 by p. So pth root of summation I equal to 1 to infinity modulus of xi to the power of p. Then ell-p is also a non-linear space, and again we have to use Holder's inequality to prove the triangle inequality. So ell-p is a non-linear space for 1 less than equal to p less than infinity. So here we note that each L1, L2, ell-p is a different vector space. In finite dimension we saw with the same R power n we defined all the p norms, but here as p varies, the vector space itself varies. So that is a difference here between finite dimension and infinite dimensional. So each ell-p is a different vector space, and each ell-p is a normed linear space. When we say ell-p is a normed linear space, it is a space of sequence. It is called a sequence spaces because the space contains all real sequences if it is a real vector space, and a complex sequences if it is a complex vector space. Normally for example purpose and for proving purpose we consider vector space over R, that is a real space of all real sequences. And addition is defined as a normal sequence addition coordinate wise, which also satisfies scalar multiplication. So ell-p will be a vector space, and if we define norms such the p norms in this manner, it will be a norm linear space with all these p norms. So now we are going to check whether ell-p is a complete norm linear, that is whether ell-p is a Banach space. So we consider a Cauchy sequence xn. It's a Cauchy sequence in ell-p where xn is given by its coordinates x1 to the power of n, x2 to the power of n, and so on. So given epsilon positive, there exists capital N such that norm of xm minus xn is less than epsilon. P norm of xm minus xn is less than epsilon for all m comma n greater than or equal to n. So for each i, modulus of xi to the power of m minus xi to the power of n to the power of p will be less than or equal to the summation, because all are positive quantities, and which is less than epsilon to the power of p, because the summation is nothing but p norm of xm minus xn raised to the power of p. So this summation will be less than epsilon to the power of p. So for each I, xi n will be a Cauchy sequence. We are following the same technique here also, what we followed in R power n. For each I, xi to the power of n will be a Cauchy sequence, and by completeness of R, we have xi n converges to xi for each I. Then, as in the case of R power, we can check that for each I we have the sequence xi n converges to xi. So we have a element in ell-p x equal to x1, x2 and so on. And also we have to check that this x belongs to ell-p. Summation I equal to 1 to k modulus of xi to the power of minus modulus of x to the power of n is less than equal to infinite summation, which is less than equal to epsilon to the power of p. Now we are taking n tends to infinity here. So by taking n tends, keeping m as it is and taking n tends to infinity, because this summation I equal to 1 to k is less than epsilon to the power of p for all m comma n greater than equal to some capital N. So we can take n tends to infinity, and we know that xi to the power of n converges to xi. Therefore summation I equal to 1 to k xi to the power of m minus xi modulus to the power of p is less than epsilon to the power of p. And since this is true for each k, each finite sum k, we can have k tends to infinity, and p norm of xm minus x raised to the power of p will be less than epsilon to the power of p, and therefore we have the sequence xn converges to x in ell-p, and so ell-p is complete. Therefore ell-p is a Banach space. Similarly, we can define the space L infinity, analogous to the maximum norm we define in R power n. So here we can define set of all sequences such as supreme of mod xi 1 less than equal to I less than equal to less than infinity, that is simply the set of all bounded sequences. So L infinity is set of all bounded sequences where the infinity norm is defined by supreme of mod xi 1 less than equal to I less than equal to infinity. Then we can show by the similar techniques ell-p is also a Banach space. So we have the Banach spaces, ell-p Banach spaces for 1 less than equal to I, for 1 less than equal to p less than equal to infinity. So these ell-p's, we call them as ell-p spaces. These ell-p spaces, they are different spaces because they are sequences with different conditions, so there will be different spaces. But we can see that for p less than r, ell-p is a subset of Lr. So for 1 less than equal to p less than r less than equal to infinity, easily we can show that infinity norm of x is less than equal to p norm of x. 1 less than equal to I less than equal to p less than infinity, because the infinity norm of x is nothing but the supreme of mod xi, and definitely it is less than equal to the p norm, which is actually the sum of the pth power of its coordinates. So now we are going to show that the r norm of x is less than equal to p norm of x for p less than r. For this we have y equal to x by p norm of x. So clearly norm of y in p norm is equal to 1. Norm of y in p norm equal to 1, and therefore each coordinate, that is modulus of xi, each coordinate of y, modulus of xi divided by p norm of x is definitely less than equal to 1, because the whole norm itself is equal to 1, and so this is a real number between 0 and 1. Therefore when we raise to the power of r, it will be less than equal to modulus of xi divided by p norm of x to the power of p. So this implies r norm of y to the power of r is equal to summation I equal to 1 to infinity modulus of xi by p norm of x to the power of r. So here we are considering r norm of y to the power of r, therefore we are having this term which is less than or equal to summation I equal to 1 to infinity modulus of xi by p norm of x to the power of p, because already we have shown that the corresponding quantities are less than satisfy the inequality, and so we can take the summation. But this term on the right hand side, summation I equal to 1 to infinity modulus of xi divided by p norm of x to the power of p is equal to p norm of y raised to the power of p, which is equal to 1. And therefore, by the definition of y, r norm of x by p norm of x. So here we are calculating the r norm of y, which is less than or equal to 1, because we have just proved that r norm of y to the power of r less than or equal to 1. So r norm of y less than or equal to 1, and therefore we have here p norm of x inside that r norm is just a scalar, so we can take the scalar outside. So we have r norm of x less than or equal to p norm of x. So whenever the p norm of a sequence is less than infinity, the corresponding r norm will also be less than infinity. Therefore, any sequence belonging to ell-p will also belong to L-r. Therefore, we have ell-p.
We are going to
subset of
C naught naught. That is the set of all.
So ell-p spaces are basically sequence spaces
0 and whose tail is also 0. That is, after some stage, all entries in the sequences are 0. So this set we call it as C naught naught. So C naught naught contains all the sequence xn such that xn equal to 0 for some n greater than 0 and for all small n greater than or equal to capital N. Then we can see that by sequence addition and scalar multiplication, C naught naught is a normed linear space with respect to any p norm, 1 less than equal to p less than equal to infinity. Because in C naught naught, each sequence, each element which is also a sequence, will have only finite entries. Therefore, any infinite summation I equal to 1 to infinity mod xi to the power of p, this will become a finite sum, and therefore in C naught naught we can define any norm. Now we are going to see whether the C naught naught is a complete metric space or not. So we construct a sequence in C naught naught as follows. Let v1 equal to 1, 0, 0 and so on. v2 equal to 1, 1 by 2, 0, 0, 0 and so on. And like that vn equal to 1, 1 by 2 up to 1 by n, 0, 0, 0 and so on. Then we can see that each vn belongs to C naught naught, because in all these elements after some stage the entries are 0. But if you want to check whether vn converges to a element in C naught naught, first we can check that vn is a Cauchy sequence under the 2 norm. So what we have to do to check vn is a Cauchy sequence under 2 norm, we have to consider vn minus vm, and vn minus vm will be nothing but summation I equal to 1 to infinity will reduce down to summation I equal to mtn 1 by I square, where I varies from mtn. And since summation 1 by n square is convergent, we know that this series is also convergent. Therefore we can verify that Vn is a Cauchy sequence under 2 norm, but this sequence converges to a sequence in 2 norm. But what will be the limit of this sequence? The limit of this sequence is nothing but the sequence 1 by n. The sequence 1 by n will be the limit of this sequence Vn in C0 but we know that 1 by n is not a member of C0 because 1 by n is a sequence converging to 0, but the tail is not 0. The tail of the sequence 1 by n will not be 0, therefore 1 by n is not a member of C0 and therefore C0 is not a complete metric space. In fact, C0 will not be complete with respect to any p norm. C0 because the same thing we can do for any p norm, and we just have to apply with the appropriate construction of Vn depending upon that p norm. So C0 will not be complete with respect to any p norm, though we can define any p norm on C0. And also each member of C0 will belong to any ell-p, because we can define any p norm on C0 and so we can consider C0 as a subset of any ell-p, and also even C0 can be considered a subset of any L infinity. And already we have seen for p less than r, ell-p is a subset of Lr, therefore we have this relation among the sequence spaces, that is C0 is subset of L1, subset of L2, subset of ell-p for any p greater than or equal to 2, and all these will be subset of C0, and where C0 is the set of all sequences converging to 0, and C0 will be a subset of L infinity because every convergent sequence is a bounded sequence, and all these sequence spaces C0, L1, L2 and for any ell-p including C0, all the sequence spaces will be a subset of L infinity, where C0 is contained a set of all sequences converging to 0. And so you can see that in a same norm, in the same vector space we can define different norm. That is what we can understand from here. Suppose we take L1. In L1 we can define either one norm or you can define any p norm. So if we just say L1, then without saying what norm it is, then we just mean that L1 is defined in one norm, and it is also possible to change the norm. So we can consider L1, though to define L1 we need that one norm. Using one norm only we are defining the vector space L1, but after defining the vector space L1 we can give or we can define any norm on L1. Similarly we can do for same also other ell-p spaces. But in C0 we can define only infinity norm, because all convergence, though C0 contains all those sequences which converge to 0. C0 contains all those sequences which converge to 0, but we know that if a series converges then the nth term goes to 0, but the converse is not true, that is the nth term may go to 0 but the series need not converge. So in C0 we cannot define any other p norm, but we can define infinity norm. So C0 will be a subset of L infinity, and also C0 will be a complete nonlinear space. That is, if you take any sequence in C0 and the limit, because we are defining infinity norm. Okay, so about this infinity norm we can see more about this infinity norm in the coming discussion, and we can see that C0 is going to be a complete norm-linear space. So C0 is also a Banach space. We can also define infinity norm on C, the set of all convergent sequences. But there is much similarity between C and C0. And because as vector spaces they are isomorphic, and instead of discussing C, we can very well define C0. So we can see that the properties of norm linear space can change if the underlying norm is altered. So a norm linear space means a vector space attached with a norm, but it is also possible to change the norm whenever required. So this is what we can understand from the infinite dimensional sequence spaces. And also, though we can define any norm on a vector space, in particular if we take the sequence spaces, we can define any norm on the sequence spaces, but if we just say ell-p means, then that means we can define only p norm. So if you are going to change the norm, suppose if you are going to change the norm, then we have to specify which norm we have to attach to the vector space ell-p. Otherwise, if you don't wish to change the norm, then we can just say it is a ell-p space. Then it is understood that the corresponding ell-p space has been defined with the corresponding p norm. So these are the basic properties about these ell-p spaces.